One. So in this class we are going to discuss about the spherical mirrors and its working. The reason why we are calling them as spherical mirrors, because if you consider some large sphere which is made up of some reflective material, and out of that a larger sphere, if you cut only a small portion of that larger sphere, this smaller removed portion is going to resemble like this, right? So exactly the same way only the concave mirror and convex mirror is also going to looks like. So that's why the concave mirror and convex mirrors are generally called as spherical mirrors. Apart from these spherical mirrors, we are also having parabolic mirror and elliptical mirrors also. But now our primary focus is only about the spherical mirrors only, which means concave and convex mirror only. So we are going to stick with that. Okay, I will tell you the clear-cut distinction between the concave mirror and convex mirror now. Okay, so as I already told you that the concave mirror and convex mirror is going to looks like this, right? So let me draw that in more detailed way. It's how a concave mirror or convex mirror is going to looks like. Imagine, and okay, if concave mirror and convex mirror both looks like the same way, then how can we distinguish concave from convex? I will tell you the differences now. In concave mirror, right, the reflection is going to take place on the inner surface of the mirror, which means you know that if you consider a sphere, right, this is called as inner surface, it's called as outer surface, correct? If the reflection is taking place on the inner surface of the mirror, that kind of mirrors are called as concave mirror. Yes, the other set of the mirrors are completely silvered, so that's why the reflection is taking place on the inner surface. Okay, and for convex mirror, the reflection is going to take place on the outer surface. It's outer surface, right? The reflection is taking place on the outer surface of the mirror, and that kind of mirrors are called as convex mirror. And in market, we are using both of these kind of mirrors in different places. For example, in barber shop they are using the concave mirror, and similarly in bike, right, or in car, as a rear mirror we are using convex mirror. So many applications these mirrors are having. Before seeing all those applications, it is better to have some ideas about some terminologies. So we will discuss about those terminologies now. After that, we can have a few more clear-cut distinction between the concave and convex mirror. Okay. What are the idea I am going to discuss now? It is applicable for concave as well as for convex mirror also. But let me say that I am going to explain this for concave mirror initially. But you should remember that, you should keep that this idea in your mind. What are the idea, what are the terminologies we are going to introduce? These terminologies are applicable for all kind of mirror, including to the plane mirror also. Okay. See, a concave mirror will be having some geometrical center, right? That geometrical center is called as pole. Similarly, okay, as I already told you before, right, concave mirror or convex mirrors are nothing but it is resembling the removed portions of the mirror, okay, which was cut down from some huge sphere, huge reflective surfaces. Okay, so in that case, if you imaginally extend this curvature, right, it could form some larger sphere. So that larger sphere should definitely have some center point. That center point is called as center of curvature. So if you imaginally connect the center of curvature and pole through a line, that line is called as principal axis. You can call this axis as a principal axis. Okay, it's an imaginary line which connects the center of curvature and poles. Okay. Similarly, I can also coin one more parameter also. I can say that if I shed any kind of light which is parallel to the principal axis, okay, on the concave mirror means after getting reflected, all those parallel rays will pass through a point, will pass through a common point. That common point is called as focal point. Okay. So we define so many things now. Pole is a geometrical center, and if you extend the curvature of the concave mirror or convex mirror, it will form a sphere. That imaginary sphere will be having some center. That point is called the center of curvature. If you connect the center of curvature and pole through a line, we will be getting a line. That line is called as principal axis. And if you shed a light on the concave mirror and along a principal axis means after getting reflected, those light rays will start to converge in, it will start to pass through a point. That point is called as focal point. So these are the some terminologies you should be very familiar with that. Okay. And we can define the same kind of things for convex mirror also, but before discussing about the convex mirror, I will also introduce the sign conventions also here. Okay. Since for most of the occasions we will be placing the objects on this side, right? We will be placing the objects on this side. So from the objects towards the mirror, the light ray is going to propagate along this way only, right? This is a light incident direction. So if any horizontal distances are measured, that should be measured from the poles only. Pole is a reference point. Okay. From the poles only, any horizontal distances can be measured. Okay. And if that horizontal distance is measured along the incident ray direction means it's a positive, and if the horizontal distance is measured in opposite sense to the incident ray direction means it's a negative. So it's a sign convention we have. Similarly, if any vertical distances are measured, it is measured with respect to the principal axis only. So with respect to the principal axis, if you measure the height along this way, we can call that height as a positive. Okay. So if any vertical distances are measured in opposite sense, which means any vertical distances are measured in downward sense, and it's a negative as per our sign conventions. So again I define the two things now. The one is, if we measure any horizontal distances, all the horizontal distances are measured with respect to the poles only, and that too, and if any distance is measured along the light incident direction from the poles, that distances are called as positive. In opposite sense, if you measure any horizontal distance means, and that distance are called as negative distances. Similarly, we have sign convention for vertical also. I hope that by this time you are having some clear idea about these sign conventions. We will be sticking with these sign conventions so that we can understand so many things. Okay. I can define the similar kind of things for convex mirror also. Okay. You should be familiar with the convex mirror also. Okay. Now I can tell you one more thing also. See, between the center of curvature and pole, we have some distance, right? That distance is called as radius of curvature. So CP, center of curvature to pole, that distance is called as radius of curvature. Okay, radius of curvature. Radius of curvature. Similarly, from the poles to from the focal point to the pole, okay, we will be having another distance. That distance is called as focal length or focus. Okay. Now we can see the relationship between the radius of curvature and the focal length. I can try to establish the relationship between these two. Okay. Consider a concave mirror now. It's a pole. It's a pole. It's the center of curvature. It's a focal point. Okay, now our task is to establish the relationship between the CP and FP, which means radius of curvature and focal length. It's what we are going to establish. Okay. Now imagine consider a one ray, right, one light ray that is parallel to the principal axis, and it is falling on our concave mirror. You know what will happen, right? After getting reflected, this light ray will pass through the focal point. Is it right? and let me call this point of incident as a M. Okay. See, usually this concave mirror is curved in shape only, but if this incoming light rays are paraxial rays, means paraxial means the light rays which are very closer to the principal axis and which are falling on the concave mirror or convex mirrors are called as paraxial rays. Light rays which are very closer to the principal axis and which are parallel to the principal axis are called as paraxial rays. So, what are the idea we are going to develop? It is strictly applicable only to the paraxial rays. Okay, you cannot obviously apply these ideas to the marginal rays also, because there the rules are different. Okay, so we can apply the rules only to the paraxial rays now. Okay, imagine it's a paraxial ray, it is hitting on our concave mirror at the point M. After getting reflected, it is going like this. Okay, at this M point we can try to draw the normal line. How will you draw the normal line to a sphere? See, if you want to draw a normal line to a sphere, right, at any point, you should join that point to the center of the sphere, because if you extend the radial line, right, the radial line is going to be the normal at this point. Okay, so using the same analogy over here, so if you want to draw the normal line over here, if you want to find out the normal line at this point M, you should draw that M point to the C. If you imaginally extend this line, you will be getting the normal line at the point M. So, it is going to be our normal line then, right. So, it is so clear, I told you before, right, it would be a plane mirror or concave mirror or convex mirror, all the mirrors will obey the laws of reflection. So, if this is an incident ray, right, if the incident ray is making some theta angle to the normal line, the reflected ray is also going to make the same theta angle to the normal line. So, the total angle made by this line is 2 theta with a horizontal, right. So, obviously if this angle is 2 theta means this angle is also 2 theta, because alternate angles are equal, right. Similarly, if this angle is theta, okay, if this angle is theta and this angle also should be theta, because alternate angles are equal, right. Because this line is called as normal line, this normal line is making theta angle to the horizontal. So, the same normal line should make the same theta angle to the another horizontal line. Okay. Now, consider this triangle. Okay, consider this triangle, two triangles. We got the two triangles here. The one is MCP triangle. The another is MFP triangle. If you consider these two triangles, you can very clearly understand one thing, right? If I take see, originally it should not be considered as a triangle because it's a curved surface, but since we have assumed these derivations for paraxial rays which are very close to the principal axis, locally we can assume it's a straight line. It's not a curved one, it's a straight line. We can make that assumption. That assumption is having its validity, of course, because we are applying we are developing some ideas which are only and strictly applicable only to the paraxial rays. Okay, so then we can consider the MCP and the MFP as a two kind of triangle. So, if from the MCP triangle I can say that tan theta is equal to opposite side MP and adjacent side CP. Similarly, from the MFP triangle I can say that tan 2 theta is equal to opposite side MP, adjacent side FP. Okay, and it is so clear that, so since we have considered paraxial rays, obviously this theta is going to be a very smaller one. Yes, this M is going to lie very closer to the P. So, for smaller angle approximation, the tan theta can be replaced with theta itself. So, theta equal to MP by CP, and similarly tan 2 theta can be replaced with the 2 theta itself. So, 2 theta equal to MP by FP. On comparing these two, you can very clearly see that in the place of theta I can substitute MP by CP into 2 equal to MP by FP. The MP will get cancelled off. I got what? 1 by FP equal to 2 by CP. So, FP equal to CP by 2. So, I got a relationship then. FP is nothing but focal length, CP is nothing but radius of curvature. So, for spherical mirror, it could be a concave mirror or convex mirror, this relationship will hold on for any kind of spherical mirrors. For all spherical mirrors, this relationship will be applicable. Okay, it's one of the important relationship we have. and apart from that we can try to develop the mirror equation now. So this mirror equation is so vital to work out the NEET questions or JEE questions. So we can see how that mirror equations are derived by using the very simple ideology. Before discussing about the mirror equation, I just want to introduce ray diagram of the concave mirror and convex mirror. So after discussing the ray diagram, it's better to analyze the mirror equations. It's better to derive the mirror equation afterwards. Okay. First we start with the image formation diagram, right? Imagine, before discussing the image formation diagram, I will tell you the rules for image formation diagram. Imagine it's a I will simultaneously tell you the rules for concave as well as for convex simultaneously. It's a concave mirror. Okay, it's a convex mirror. I will tell you all the rules simultaneously for both of these mirrors. If any light ray, it's a center of curvature, it's a focal point, it's a pole. It's a pole, it's a focal point, it's a center of curvature. Okay, if any light ray that is coming parallel to the principal axis, after getting reflected, it will pass through the focal point. It's a rule 1. Okay, rule 1. And in convex mirror, right, if any light ray that is coming parallel to the principal axis, after getting reflected, okay, that light ray will seems to be going in such a way that as though it is emanated from the focal point. Okay, if you imaginally extend this line backward, it seems to be coming from the focal point. It's a rule 1. It's a rule 1 for concave mirror as well as for convex mirror. Okay. Now we can see the rule 2. If any light ray that is directed towards the center of curvature, and if it's meeting on the concave mirror, after getting reflected, that light ray will exactly retraces its own path. It's a rule 2. Okay, and we can draw the same rule for convex mirror also. If any light ray is directed towards the center of curvature, after getting reflected, those light ray will retraces its own path. It's a rule 2. And we can draw the rule 3 also. Rule 3. Rule 3 is nothing but it's a inverse of the rule 1. If any light ray is directed towards the focal point, after getting reflected, it will become parallel to the principal axis. Imagine this light ray is directed towards the focal point. After getting reflected, it will become parallel to the principal axis. So it's a rule 3. Similarly, here also we can draw the similar kind of rules. If any light ray is directed towards the focal points, after getting reflected, the reflected light ray will become parallel to the principal axis. It's a rule 3. Okay, and the rule 4. If any light ray is directed towards the pole, okay, after getting reflected, right, whatever the angle that light rays are making with the principal axis, the reflected light ray will also make the same angle. It's a rule 4. Okay, so I will draw the rule 4 also here also. And any light ray is directed towards the pole, after getting reflected, the reflected ray will make the same angle with the principal axis. So these are the 4 rules we have. Okay, and by completely using any two rules, we can able to get the locations of the image and nature of the image also. Okay, once if you are so thorough with these rules, you can able to construct the image formation diagram on your own now. Okay, I will draw the image formation diagram for concave mirror. Imagine the first condition, if the object is placed at infinity, if object is located at the infinity, from the distant objects, the light ray, if any light ray is coming from the distant objects, those light ray seems to be parallel to each other, right? It is logically easy to visualize because I told you that before. From the sun, in all the direction light rays will emerge out. It has a tendency to diverge out near to the surface of the sun, but from the sun at very far away, right? So at this place the light rays are nearly parallel. So you can make use of the same assumption here. If object is located at very far away from the concave mirror, from that object whatever the light ray is coming and approaching our concave mirror can be treated as a parallel. So these parallel light rays, after getting reflected, we know the reflected ray will pass to a focal point. So the image will be formed exactly at the focal point. If the object is located at the infinity, the image will be formed at the focal point. Okay, it's a thing we have. So and also, since at the focal point the light rays are converged in, so the formed image will be having diminished size, which means it will be having zero size. It will be like a point sized. Again we can consider another situation. This time again we have a concave mirror, but it's the center of curvature, it's the focal point. Okay, this time object is not located at the infinity, but it is located at some finer distance. So object is located at beyond C condition. So beyond C. So it's the center of curvature. So beyond C object is located, right? So now our task is to find out the image locations and the nature of the image also, nature of the formed image also. So to get it, I can make use of the 4 rules we discussed. Okay, from the top tip of the objects we can consider one light ray that is coming parallel to the principal axis. After getting reflected, the reflected light ray will pass to the focal point. It's rule 1. I can consider one more rule also. If I draw any light ray from the top tip of the object in such a way that it is directed toward the center of curvature, after getting reflected, it will exactly retraces its path. So these 2 reflected light rays are meeting at this point, right? So that's where the final image will be formed. Okay, that's why the final image will be formed. So we can see very clearly when the object is placed beyond C, the image is formed between the C and F, and the size and the nature of the images are real image and it's an inverted image, because here we have the arrow mark pointed upwards, but here the arrow mark is pointed in downwards sense. So it's an inverted image. So real in the sense, if I place a paper over here, I can be able to hold the images on the paper. I can able to project the images onto the paper. So that's why these kind of images are called as real images. So it's a real, inverter and diminished. So comparatively speaking, with the height of the object, height of the image formed is somewhat smaller. That tells you that the image is diminished in size. Okay, now we can see the other cases also. If object is placed exactly at the C, the case is entirely different now. If object is placed exactly at the C, okay, to get the image locations, again we can use any 2 rules. One rule, I am making use of the first rule now. From the top tip, I consider a light ray which is parallel to the principal axis. After getting reflected, these light rays are passing through the focal point. It's rule 1, I applied it successfully. Now I can apply the rule 3 or rule 4. I can apply any two rule, right? So I can apply the rule 2 now. If I consider another light ray and if it is directed towards the focal point, after getting reflected, this light ray will become parallel to the principal axis, correct? So the final image, see these 2 reflected light rays are meeting at these locations only. So that's where the final images are formed. So if you look into this image, right, you can see very clearly object size and image size are nearly identical, right? It's same. So what we got? We got a real, inverted and The formed image is having the same size as that of object. Okay, same size. Okay, we can consider one more case also. If object is placed between the C and F, then cases are different. From the top tip of the object, I can consider one light ray. After getting reflected, the light rays will be passing through the focal point. Apply the rule 1. I can consider one more rule also. Okay. From the top tip of the objects, I have drawn a line. So if I extend that backwards, it seems to be coming from the center of curvature. So this light ray, after getting reflected, will actually retraces its own path. So these two reflected light rays seems to be meeting somewhere. You can see that they seems to be meeting somewhere. Okay. So it's where the images will be formed. So we can see very clearly here. So here we got a real image and inverted image, but formed image is somewhat bigger than an object. Is it right? So when the object is placed in between the C and F, the finally formed image is somewhat bigger than the object itself. Okay, it's another thing we have, and we have one more case also on that. Center of curvature, focal point. If I place a object exactly at the focal point, okay, then the image is going to be formed at the infinity. I will tell you the reason for it. We are apply the rule 1 now. From the top tip, I consider one light ray which is parallel to the principal axis. After getting reflected, these light rays are passing through the focal point in this way. Okay, I can consider one more light ray also. Let me apply the rule 4 now. It's the rule 4. If you apply the rule 4, you can see very clearly here, both of these reflected light rays are parallel to each other. So you know that parallel lines will never meet, right? So, and there is a statement in mathematics, parallel lines seems to be meeting at the infinity. See, if you look into the railway tracks may seems to be parallel, but if you look at the vantage point, which means if you look at the very distant point along the railway track, there those parallel railway tracks seems to be meeting. The same assumptions we can make here, since these light rays, reflected light rays are parallel to each other, we may assume they may appears to be meeting at the infinity, so that's where the final images will be formed. So we can assume the final images are formed at the infinity, and the final image will be having enormous size. It will be extremely magnified. So if the object is placed at the focal point, the image is real, inverted, and it is extremely magnified. Extremely magnified. And we can consider one more case also. It's a last case we have. Again, consider concave mirror. It's a very specific case, okay, of a concave mirror, because in all the other cases the concave mirror has produced real images only, except for this case. Only for this case the concave mirror is going to produce virtual image. So try to understand this very clearly. It's a center of curvature, it's a focal point, it's a pole. If I place an object very closer to the concave mirror, which is between the F and P, if I place the object means, then let me try to find out where the images are formed. From the top tip, I can assume one parallel light ray parallel to the principal axis. After getting reflected, this light ray will pass through the focal point. I can apply the rule 4 also now. If I apply the rule 4, this light ray after getting reflected, it will go like this. See, if you look at these two reflected light rays, they seems to be diverging away from each other. So if those reflected light rays are at least parallel, we can assume they seems to be meeting at the infinity. But if they are diverging in nature, they will not definitely meet on this side. So obviously then to get the image locations, we can imaginarily extend them backwards. you can imagine extend them backwards. They seems to be meeting somewhere inside of a mirror world. It's a mirror world actually. Okay. So this is where the final images are formed. So you can see that here the final image is erect. Erect in the sense, here if the arrowhead is pointed upwards, the finally formed image in finally formed image also the arrowhead is pointed upwards. So the image is erect in nature and it's virtual. The reason why I am calling it as virtual is because this image is formed into the mirror world, mirror dimension, because it seems to be located into the mirror at some distance away. So that's why these images are called as virtual image, because you cannot able to hold the image on your hand, you can able to project that image onto any pages. So that's why these images are called as virtual images. So we got a virtual, erect and magnified images. So in note on this, it is for this purpose, right? Dentist and in barber shops, they are using the concave mirror, because when the mirror is placed very closer to your face, right? You and obviously the concave mirror can produce the virtual, erect and magnified image. So obviously the dentist requires the magnified images of your tooth so that they can able to perform any kind of operations on them. Is it right? So it is for that purpose they are using the concave mirror. Okay. Similarly, we can see the image formations of the convex mirror also by applying those rules. Image formations of the convex mirror. Okay, consider this. It's a focal point, it's the center of curvature. Here we have a object. From the object, right? See, this object would be placed anywhere. It would be placed at any finite distance from the convex mirror, and if it's placed at any finite distance, the image locations can be pinpointed by using the ray formation diagram, image formation diagram. I will apply the rule 1 first. I can draw one light ray which is parallel to the principal axis. After getting reflected, right, I told you the rules, right? After getting reflected, this light ray seems to be coming from the focal point if you are backwardly extending the means. Okay, and I can apply the rule 4 also. Okay, it's a rule 4. It's the incoming light ray, it's a reflected light ray. So if you focus on the two reflected light rays, 1 and 2, these two reflected light rays seems to be meeting somewhere into the mirror. That's where the images will be formed. So for convex mirror, if object is placed at any finite distance, the image will be formed between the focal point and pole. And the nature of the image is, it's a virtual image. Yes, that image is formed into the mirror world. It's a mirror world. Virtual and erect and diminished in size. What will happen if the object is placed at an infinite distance from the convex mirror? Again, the same rules are applicable. If the object is placed at the infinite distance from the convex mirror, whatever the light ray that was reflected off from the object may considered to be a parallel. May be considered to be a parallel because I told you the logics for that, right? So these light rays after getting reflected, right, they seems to be coming from a focal point. So the image is going to be formed exactly at the focal point itself. If object is placed at infinity, the convex mirror is going to produce the image exactly at the focal point, and the finally formed image is going to be a point sized. So these are the image formation diagram we have. Okay. Now having developed enough ideas about the nature, location and size of the image formed by the concave and convex mirror, now we have enough idea to develop the mirror equations. Okay, now consider we are going to develop the mirror equation now. So, to develop this, first we can consider a concave mirror. So, concave mirror, here we have a pole and it is a focal point, it is the center of curvature. Let me assume we placed an object at buoyancy conditions. We know what will happen, where the image will be formed, right? We have discussed that just now only. So, but now we can develop the mathematical equation for it. Okay. From the top tip of the objects, we can consider one light ray which is parallel to the principal axis. After getting reflected, that light ray will pass through the focal point. Okay. We can consider one more light ray also. We can apply the rule 4 now. Okay. If you apply the rule 4, this is the incident ray. This incident ray is making some angle. Let me call this angle as a theta. Okay. To the principal axis. After getting reflected, the reflected ray is also going to make the same theta. So, these two reflected rays are meeting at this location. That is where the final images will be formed. Okay. Okay. Now, consider these triangles. Let me call this point as a M. Okay. So, the MP is approximately can be treated as a straight line, even though it is a curved one, approximately we can treat it as a straight line. So, if you consider MFP triangle, okay, and B dash F A dash triangle, consider these two triangles. These two triangles are identical triangles, right? Yes, they are making the same angles. It's I means it's also I. Is it right? So, then I can say that tan I is equal to what? Tan I is equal to MP by FP. Similarly, the same tan I is equal to A dash B dash by B dash F. And I can very clearly tell that since MP is assumed to be a straight line, so the MP length is approximately equal to what? AB length. Is it right? So, MP can be replaced with AB. So, I got a AB by FP equal to A dash B dash by B dash F. Okay. Now, I can try to rearrange this into this form. I can say that A dash B dash by AB equal to B dash F by FP. Okay. I got the equation 1. Let it be. It is equation 1. Okay. Similarly, consider these two triangles APB and A dash P B dash. Consider these two triangles. You know that these two triangles are identical triangles, right? So, again I can write tan theta is equal to opposite side AB, adjacent side BP. The same tan theta equal to opposite side A dash B dash, adjacent side B dash P. So, again I can able to rearrange them into this following form: A dash B dash by AB equal to B dash P by BP. Okay. So, it is equation 2. Consider equation 1 and equation 2. The left hand sides of the equations are identical. So, the right hand side also should be identical. So, I can say that B dash F by FP should be equal to B dash P by BP. This B dash F can be replaced with what? It is a B dash F, right? It is a B dash F. It is a B dash F. The B dash F can be replaced with what? B dash F is equal to B dash P minus FP. So, B dash F can be replaced with B dash P minus FP by FP equal to B dash P by BP. Okay. I got an equation like this. So far we got these ideas very clearly now, right? Now whatever the thing we got here, it's merely a distances, but we are going to give the sign conventions now. So far imagine this very clearly. I have B dash P, FP, B dash P and FP, all those quantities are merely distances, but now I am going to give the sign conventions to them. I am going to assign some signs to them. So that is why whenever we are using the mirror equation, we should use them along with the proper sign conventions. So I can say that B dash P is nothing but this distance, right? B dash P, this distance, it is nothing but image distance. Let me call this image, it's image, right? It's image. So B dash P is nothing but image distance. I can call it as a V. Generally I can call it as a V, but as per our sign conventions, it's a minus of V. Is it right? Because this is the incident ray direction. From the poles, if you measure any horizontal distance along the incident ray, it should be a positive. From the poles, if you measure any horizontal distance in opposite sense to the incident ray, it's a negative. Since the B dash P is measured in opposite sense to the incident ray direction, so it should be a minus of V. Similarly, BP is nothing but object distance, it is also minus of U. Similarly, FP is nothing but focal length, it is also minus of F. Let me replace these quantities over there. So B dash P is nothing but minus of V, FP is nothing but minus of F, FP is nothing but minus of F, equal to B dash P is nothing but minus of V, BP is nothing but minus of U. If I simplify this, I will be getting equations like minus of V plus F by minus of F equal to V by U. Okay, and if I take this minus to the numerator, I will be having V minus F by F equal to V by U. Okay, so I can simplify this into this following form: V by F minus 1 equal to V by U. So V by F plus minus divide the whole equations by V, so that you may have what? 1 by F minus 1 by V by 1 by U. So what I got? 1 by F equal to 1 by V plus 1 by U. So we got a mirror equation. This equation is generally called as mirror equation. We will be using that mirror equation. You can use this mirror equation to understand even the plane mirror also. I will tell you that later. Right now you can understand this. This mirror equation can be used for any kind of mirrors, any kind of mirror. It can be plane mirror or spherical mirrors. We can readily apply these mirror equations. But when we are using this mirror equation, you should use them with appropriate sign conventions. If you are blindly using that equations without using the proper sign convention, means obviously this mirror equation will give you the wrong results. Now we can see the magnification relationship also. Okay, magnification, you know that look into this diagram. Magnification means, by the word we are telling, we are comparing in relative to the object size, how much larger the image is or how much smaller the image is. So we are comparing the size of the object with the size of the image. That comparison is called as magnification. Okay, so I can say that magnification is equal to height of the image divided by the height of the object. In that case, height of the image is negative because it is measured downwards. So I can say that height of the image is negative, minus of HI as per our sign convention, and height of the object is positive, so it is a HO. So magnification is equal to this, and I can very clearly write, consider this triangle, you can see very clearly here. From this equation you can very clearly infer one remarkable fact: A dash B dash is nothing but height of the image, AB is nothing but height of the object, whereas B dash P is nothing but image distance, it is a minus of V, BP is nothing but object distance, it is a minus of U. So the minus will get cancelled off. As per our sign conventions, HI by HO equal to minus of V by U. So this is the magnification formula then. So I can say that magnification is equal to what we got. Magnification is equal to HI by HO, which is equal to minus of V by U. It's a magnifization formula we have. Okay, remember these magnifization expressions also. Sometimes we can try to write these magnifications in terms of the object distance and in terms of the image distance also. How can we able to write that? Just consider this is a mirror equation, multiply the entire equation with the u on either side, you will be getting a u by f equal to u by v plus 1. Is it right? And bring this 1 to the side, you will be getting u by f minus 1 equal to u by v. So, you got what? U minus f by f equal to u by v. So, what I got here? I got a v by u equal to f by u minus f. So, but we know the expression for magnifization. Magnifization is minus of v by u. So, it is a minus of f by u minus f. I can able to rewrite the same as f by f minus u. So, it is a magnification in terms of the object distance. Magnification in terms of u. Similarly, if you multiply the entire mirror equations with v on either side, you can able to get the magnifications in terms of v also. Just take this equation, take this mirror equation and multiply this equation with v on either side. So, we will be getting v by f equal to 1 plus v by u. What you got? I got a v by f minus 1 equal to v by u. So, v minus f by f equal to v by u. So, it is a magnification expression we got. Okay. So, magnifications in terms of v, magnifications in terms of u. I hope that you can able to understand these formulas very clearly, right? Okay. Now, once if you got this idea very clearly, we can understand the aerial magnifications and the lateral magnifications also. Now, we can develop the lateral magnification formula also. Lateral magnification. Consider it is a concave mirror. I placed the object over here. The object is having the height of h naught and its length is du. We can assume like that. So, let us say that its image is formed over here. The image is having the height of hi and it is having the length of dv. Okay. And we know from the mirror equation 1 by f equal to 1 by u plus 1 by v. Okay. You try to write these equations in terms of its inverse form, f power minus 1 equal to u power minus 1 plus v power minus 1. Okay. If you try to differentiate these whole equations with respect to the u, I will be getting this. F is a constant. If I try to differentiate that with respect to the u, I will be getting the 0. If I try to differentiate the u with respect to the u, I will be getting a minus of 1 u power minus 2. And if I try to differentiate the v with respect to the u, I will be getting a minus of 1 v power minus 2 into dv by du. So, and on simplifying this, I will be getting u power minus 2 equal to minus of v power minus 2 dv by du. Okay. And if I bring this parameter to this side, I will be getting u power minus 2 v power minus 2 minus equal to dv by du. Okay. And I can bring this u to the denominator and v to the numerator by inverting its powers respectively. So, I will be getting a v square by u square equal to dv by du. So, dv by du it is nothing but dv is nothing but finally formed image's lateral dimension. Similarly, objects lateral dimensions. So, dv du we know the relationship between them. So, it is called as lateral magnification. So, we got the lateral magnification formula done. So, lateral magnification is equal to minus of v squared by u squared, and we know that v by u minus of v by u is nothing but linear magnifications or longitudinal magnifications. So, it can be written as lateral magnification is equal to minus m square. Okay. M is nothing but longitudinal magnifications. So, this is the relationship between them. Similarly, we can develop the expression for aerial magnifications also. Imagine we are going to develop the expression for aerial magnification. consider this. Here we have object, its dimensions are A and B, okay, and again its image is formed over here. Its dimensions are, let us say that its dimensions are magnified by m times, because its let us say that magnification is m at this location. So, we know very clearly aerial magnification is nothing but area of the image by area of the object. We can write area of the image as MA into MB, area of the object is AB. So, B will get cancelled off m squared. So, aerial magnification is nothing but aerial magnification is equal to m squared. I suppose that you can able to understand all the derivations I derived today. Now, we can focus on the numericals. Okay, now we can work out some numericals on spherical mirrors. Okay, look into the first question, 14th question. Which of the following mirrors can form real images? I told you very clearly the plane mirrors and the convex mirror will always produce virtual images only. Unless the object is virtual, it will always produce virtual images only. So, to produce only a concave mirror can produce real images. Okay. So, option C should be the answer. Now, look into the question number 15, focal length and radius of curvatures. அது ரெண்டுக்குமான ரிலேஷன்ஷிப் என்னன்னு கேட்குறாங்க. We know very clearly the f equal to r by 2. Okay. Okay, now look into the question number 18. Question number 18. Magnification of the image when the object is placed at a distance x from the principal focus of the mirror of focal length f. So, magnifications in terms of the focal length they are asking. Sorry, magnifications in terms of the object distance they are asking. Now only we derive that, right? Magnifications in terms of object distance. What is that? M equal to magnifications in terms of object distance. M equal to f by f minus u. So, f by f minus u. It is a magnifications in terms of the object distance. Okay, and so here object distance is given as x. So, I can write f by f minus x. So, I can able to rewrite the same as 1 if I take f as a common factor here, I will be having 1 minus x by f. Is it right? This f will get cancelled off. So, m equal to 1 minus x by f whole power minus 1. It can be replaced with 1 plus x by f. No. Okay, let me imagine we have some mirror, some spherical mirror. It's a focal point. Magnification of the image when an object is placed at a distance x from the principal focus of a mirror of focal length f. So, it's where we place objects. X is nothing but object distance from the focal point. So, from the poles the total object distance is called as what? F plus x. So, as per the sign convention u equal to minus of f plus x. Okay. So, we know the magnification formula then. Magnification in terms of object distance, it can be written as m equal to, what is that? M equal to f by f minus u, f by f minus u. And and I have considered the concave mirror here. So, then focal length of the concave mirror is minus f minus of u minus of minus plus I rho. So, it is a f plus x. If I simplify this, I will be getting minus f by x. So, it should be answer then. Okay. So, magnitude I can see that it is f by x. So, option C should be the answer. Okay. Now we can look into the question number 19. We have a concave mirror, its focal length is 15 centimeter. A square wide of 1 centimeter is placed perpendicular to the principal axis. So, we have a square. That square is placed perpendicular to the principal axis at a distance of 20 centimeter. So, at a distance of 20 centimeter, this distance of the distance is 20. The area enclosed by the image of the wire. We know the aerial magnetization formula, right? What is that? Aerial magnetization is equal to, the square is having a side length of 1 centimeter. So, aerial magnetization formula we know readily. Aerial magnetization is equal to m square, right? Aerial magnetization is going to be equal to m square. To get the m value, we can use this formula then. M equal to we know the u, we know the f. So, m value can be calculated by using this formula again, once again. M equal to f by f minus u. It is a concave mirror. So, focal length is minus f. While substituting the f value, we can put the minus. Okay. So, it is a minus of 15 divided by minus of 15. Object distance is already negative. So, it is a minus of 20. So, what I got a minus of 15 by minus 15 plus 20, it is a 5, right. So, I got a minus 3, magnetization value is minus 3. So, aerial magnetization value is equal to 3 square, which is 9. So, it is a 9 centimeter square. Okay. Now, look into the question number 21. So, we have a concave mirror of focal length f. Okay, the near end of the rod, see we have an infinitely long rod, right? We have infinitely long rod. So, the near end of the rod is at a distance of x from the mirror. So, that x is greater than f. So, it is a near end, it is a further end. The further end is located at the infinity. Okay, it is a near end. And then if this is the object, then length of the image will be equal to what? It is what they asked. Okay, how can we find this? We know that if you consider the another end of the object, right, which is located at the infinity, its image is going to be formed exactly at the focal point. Yes, we have already learned that thing, right. So, if the object is located at the infinity, its image is going to be formed exactly at the focal point. So, let me call the two ends of the rod as A and B. So, the A's image is going to be formed at the F. So, it is A dash, and B is located beyond F. Okay, B is located at beyond F. Let me assume arbitrarily some certain distance. Let me consider, we can make use of the mirror equation here. 1 by V plus 1 by U equal to 1 by F. It is a mirror equation, and 1 by V, you know that U is, if you consider the Bn, right, it is located at some distance beyond F, right. So, U value we can assume it is a minus 1.5 F, okay, minus 1.5 F. So, then for concave mirror the focal length is also negative, minus F. So, by simplifying this I can able to get, no, instead of taking this we can do this sum this way. We know that we do not know at what location the B is located. So, we can call this distance x. So, as per the relationship we discussed, U is equal to minus of x and F is equal to minus of F. So, if I simplify this I will be getting a 1 by V equal to 1 by x minus 1 by F. I got what? F minus x by Fx. So, V equal to, I got Fx by F minus x. Okay. And we know that beyond f conditions we cannot have the virtual image, so the image has to be a real one. So for real image we should be having this v value in negative. So for that purpose we can multiply the whole thing with minus on numerator as well as on the denominator. So fx by x minus f, it's a v value we got, right. So this v is nothing but the b, the image b's position, okay, and image a's position we already know, it is located exactly at the f, right. So we got the image b's position also, it's a b dash, so it's a b dash position, it's a b dash position, and we know the way to calculate the length of the image. Length of the image is equal to what? Take the value alone, okay, take the value alone. Now b dash position is, we know b dash position is this, fx minus x minus f, and we know the a dash position also, a dash position is f. Subtract these two and you will be getting what? Fx minus xf plus f square by x minus f, which is equal to length of the image. I got f squared by x minus f, it should be the length of the image. Is it possible for you to understand this? Okay. Now look at the question number 22. So we have a concave mirror, its focal length is given as 30 centimeter. Object is placed at 20 centimeter away from the concave mirror. Object is moving toward the mirror at the speed of 5 meter by second. So velocity of the image with respect to the ground, we should get it. And how can we get that? And I will tell you the way to calculate that. See, generally we know very clearly for spherical mirrors, the mirror equations are always be applicable. So v power minus 1 u power minus 1 equal to f power minus 1. I can able to write this in this way. If you differentiate this whole equation with respect to the time on either side, I will be getting like minus 1 v power minus 2 dv by dt minus 1 u power minus 2 du by dt equal to 0, because focal length is not going to change with respect to the time. So I got what? Velocity of the image v power minus 2 minus, I can take this whole quantity to that side. So I will be getting like u power minus 2 velocity of the object. So velocity of the image is equal to u power minus 2 by v power minus 2 v naught minus, I can invert the power by bringing them to the numerator and denominators. So by if I take the v to the numerator and u to the denominator, I will be getting like v square by u square into v naught. This is the relationship we got between the velocity of the object and velocity of the image for spherical mirrors. Okay. Right now we should get the image position priorly to use this formula. So for that purpose I am using the mirror equation, 1 by v plus 1 by u equal to 1 by f. Okay. So 1 by v, here object is located over here, so I can say that this distance is negative as per our sign convention. This is the minus of 20, and f focal length is also negative for concave mirror. So what I got, 1 by v equal to minus 1 by 30 minus 1 by 20. Is it right? Minus 1 by 30, sorry, it's plus, right? So plus 1 by 20. And simplifying this, I'll be getting like minus 2 by 60, 3 by 60. I got a 1 by 60. 1 by v equal to 1 by 60, v equal to 60. Once I got the v, I can substitute this v over there. What I got, vi equal to, v value is 60 square, u value is 20 square, right, 20 square and velocity of the object we know it's a 5. So on simplifying this we may get the answer 60 into 60 by 20 into 20 into 5. So this 0 0 0 0 will get cancelled off, it's a 3, it's a 3. So 9 into 5 45, so it's a 45 meter by second and minus. So if the image velocity is treated as positive, then if the object velocity is treated as positive, then the image velocity is going to be a negative. So but anyhow magnitude is going to be a 45 meter by second, it approaches the mirror, which should be the answer. Now consider question number 24. For a spherical mirror, the graph of 1 by v versus 1 by v they are asking. We know the mirror equation 1 by v plus 1 by u equal to 1 by f. Is it right? 1 by f is a constant. So I can very clearly tell that 1 by v equal to constant minus 1 by u. It's a relationship we got, right? So if you plot the graph between the 1 by v and 1 by u, then how come the graph is going to look like? As the u value is increasing, as the 1 by u value is increasing, from the constant you are subtracting this, so the 1 by v value is going to reduce, okay. So this equation is appearing to be a straight line because we can very clearly see that here 1 by v can be treated as a y and 1 by u can be treated as a x. So y equal to mx plus c. So it takes the form of this. So obviously the graph is going to look like this, but here in front of the x we have the slope. So similarly in front of the 1 by u we have the slope value is minus 1. So I think it should be a downward graph. Yes, slope should be a minus 1. This should be the answer then. Now we can work out some problems from convex mirror also. Look into the question number 26. We have a convex mirror, okay. Object is placed at 20 centimeter from the pole of the convex mirror, and the focal length of the convex mirror is 20 centimeter. Image is produced at what? So we can make use of the mirror equation 1 by v plus 1 by u equal to 1 by f, and object is placed over here, right? So it's a light ray incident direction from the pole. If you measure the horizontal distance in this way, it's a positive. If you measure the horizontal distance in opposite sense to the incident ray, it's a negative. So as per our sign convention, and 1 by v u is minus 20 whereas f is plus 20. I got a 1 by v equal to 1 by 20 plus 1 by 20. I got a 2 by 20 which is 1 by 10. So v equal to 10 centimeter. It should be answer. Okay. Look into the question number 28. Magnification produced by the convex mirror is 1 by 3rd. Then distance of the objects from the mirror. We know the formula m equal to f by f minus u. It's a magnifications in terms of the focal magnifications in terms of the object distance, right? For a convex mirror, the focal length is positive. So if the magnification value is 1 by 3, we should find out the distance of the objects from the mirror, right? So f into 3 equal to f minus u. So 2f equal to minus u. So f equal to minus u by 2, or they are asking u one value only. So u equal to minus of 2f. So they are asking the value alone. So u equal to 2f. This should be the answer. Okay, now we can work out previous year JEE questions also. See, look into the question number 5, and this should not be even be asked in JEE main question because it's such a simple question. The focal length of the convex mirror is related to the radius of the curvature. So you know that f equal to r by 2. It's a relationship we have. Okay, it's a relationship we have. Look into the question number 6. So they have given the figure. If you look into this picture, you can very clearly understand one thing. Okay, here diameter of this imaginary sphere is 16. So radius is 8 centimeter. So radius of curvature is 8 centimeter. I can very clearly tell that radius is equal to 8 centimeter. If the radius is 8 centimeter, I can tell the focal length also. Focal length is 4 centimeter. Okay. So image is placed exactly at what location? So image is placed at 10 centimeter, and it's a concave mirror obviously. So they are asking the position and the nature of the image. Okay. So we can readily use this formula, 1 by V plus 1 by U equal to 1 by F. It's a concave mirror, so I can say that focal length is negative and object distance is also negative. Object distance is minus of 10, whereas the focal length is minus of 4. Okay. So what I got, 1 by V equal to 1 by 10 minus 1 by 4. On simplifying this, I will be getting like a 4 by 40, 10 by 40, it's a minus 6 by 40. So it's a V. I got a V equal to 40 by 6 minus. So on simplifying this, I can tell very clearly. So the V is negative, which tells you that the image is real image, because the finally formed image is located on this side. That's why V is negative. Okay. So that tells the finally formed image is a real image, and obviously it should be inverted images also, and we can tell the magnification values also. Yes, we know that V value and M value. So out of this we can able to tell the magnification value, M equal to minus V by U. So V minus 20 by 3, U value is minus 10, right? It's a minus of 10. On cancel offing this, I'll be getting like a 2 by 3. Magnification is 2 by 3. So it's somewhat shrinked, right? So it's an inverted, real and magnified. Okay, that should be the answer. So thank you all for listening to the lecture to the full. Thank you everyone.